Dear students, we are discussing the second unit of Topology 2, and actually it is the separation and countability axioms. Anyway, the first section we have already discussed, that is T0, T1 and T2 spaces. And today I am giving the notes on the second section of it, that is what are regular and completely regular spaces. We can discuss now in a neat way. That is, first we start with the definition. That is T3 spaces we are discussing first. That is a T1 space, X2 is said to be a regular space or T3 space, provided that whenever C is a closed subset of X and P is an element of X minus C, there exists disjoint open sets U and V such that P is in U and C is subset or equal to V. This is what the definition. That is a T3 space, or it is a regular space. We call it as a regular space. The basic condition, it must be a T1 space. A T1 space is said to be a regular space or T3 space. What is condition? Provided that whenever C is a closed subset of X and P is an element of X minus C, that is its complement outside it, then there exist disjoint open sets U and V such that P is in U and C is subset or equal to V. Theorem, first theorem we can see. A T1 space X2 is regular if and only if for each member P of X and each neighborhood U of P, there exists a neighborhood V of P such that V bar is subset or equal to U. This is the first theorem. We can discuss the proof of it. That is, what is given T1 space X2 is regular. So, it's a necessary and sufficient condition we have to prove. So, suppose that X2 is regular, the first part. And what else given? That P in X and U be a neighborhood of P. Then, X minus U is a closed subset of X and P is not an element of X minus U. Okay. But X2 is regular. Therefore, there exists disjoint open sets V and W such that P is in V and X minus U is subset or equal to W. This follows from the definition of a regular space. Here, V intersection W is equal to 5, which implies V is subset or equal to X minus W, which implies V bar is subset or equal to X minus W bar, and X minus W is already closed, so X minus W bar is X minus W. This implies V bar is subset or equal to X minus W. That is first result. We have X minus U is subset or equal to W. This implies X minus W is subset or equal to X minus U. That is U. This implies X minus W is subset or equal to U. It is second result. From 1 and 2 it follows that V bar is subset or equal to X minus W, which is subset or equal to U. That is, there exists a neighborhood V of P such that V bar is subset or equal to U. This is the first part. Now conversely, suppose that for each member P of X and each neighborhood U of P, there is a neighborhood V of P such that V bar is subset or equal to U. What do we have to prove? We have to prove that X2 is regular. Let P in X, taking a point P in X, and C be a closed subset of X such that P is not an element of C. Then X minus C is a neighborhood of P. This implies there exists a neighborhood V of P such that V bar is subset or equal to X minus C by assumption. This implies X minus C is subset or equal to X minus V bar. This implies C is subset or equal to X minus V bar, which is an open set. Hence, V and X minus V bar are disjoint open sets containing P and C respectively. That is the definition of regularity, or this implies X2 is a regular space. That is the first theorem. Next, a remark is given. Every T3 space, every regular space is a T2 space, a Hausdorff space. Proof. Let x2 be a T3 space. Let small x and y be two distinct points of x. Then set y, singleton set y, is a closed subset of x, and small x is not an element of set y. As x2 is a T3 space, there exists disjoint open sets u and v such that small x is in u and singleton set y is subset or equal to v. That is, small x is in u and y in v, where u intersection v equal to phi. Hence, x2 is a T2 space, a Hausdorff space. Next theorem is an important theorem. Regularity is a topological property. We can discuss the proof. Let x2 and yu be topological spaces, and let f from x to y be a homeomorphism. Assume that x2 is a regular space. What do we have to prove? We have to prove that yu is regular. Clearly, yu is a T1 space because x is a T1 space and f is a homeomorphism. Let P in y and let C be a closed subset of y such that P is not in C. F inverse C is a closed subset of x, or F inverse C is closed in x2 because f is continuous. Also, F inverse P is not an element of F inverse C. Moreover, x2 is a regular space. Therefore, there exist distinct open sets u and v such that we can say disjoint open sets because that's what I meant. You check it properly. As x2 is regular, there exists a disjoint open sets u and v such that f inverse p is in u and f inverse c is subset or equal to v. This implies p is in f of u and c is subset or equal to f of v. But f is open. Therefore, f of u and f of v are open in y. Hence, f of u and f of v are disjoint open sets in yu containing p and c respectively. This implies yu is regular space. A topological space yu is a regular space, or regularity is a topological property. Next theorem, a subspace of a regular space is always regular. Subspace of a regular space is regular. Proof. Let x2 be a regular space and let A tau A, subspace topology tau A, be a subspace of x2. We have to prove that A tau A is regular. The space A tau A is regular, we have to prove. Let P in A and let C be a closed subset of A such that P is not in C. Now C is closed in A tau A. Now C is closed in A tau A. This implies C equal to D intersection A for some closed set D in X. If the point P is in D, then P is an element of D intersection A, which is equal to C, which is impossible. Hence, P is not at all in D. But x2 is regular, therefore there exists disjoint open sets u and v in x2 such that P is in U and D is subset or equal to V. This implies P is in U intersection A and C equal to D intersection A, which is subset or equal to V intersection A. Here U intersection A is an element of tau A, V intersection A is an element of tau A, and whether they are disjoint, U intersection A intersection V intersection A equal to U intersection A intersection A is equal to phi. Hence, A tau A is regular. Next theorem, that is, a T1 space x2 is regular if and only if for each P in X and each closed set C such that P is not in C, there exists open sets U and V such that C is subset or equal to U, P in V and U bar intersection V bar equal to phi. It's an important theorem. A T1 space X2 is regular if and only if for each P in X and each closed set C such that P is not an element of C, there exist open sets U and V such that C subset or equal to U, P in V and U bar intersection V bar equal to phi. We can discuss the proof of it. What is given? Suppose that X2 is regular. Let P in X and C be a closed set such that P is not in C. Then X minus C is a neighborhood of P. Then we are discussing the previous theorem. What is the previous theorem? Statement is given here in brackets. A T1 space X2 is regular if and only for each member P of X and each neighborhood U of P, there exists a neighborhood V of P such that V bar is subset or equal to U. You are using that theorem, and by the theorem there exists a neighborhood W of P such that W bar is subset or equal to X minus C. Here W is a neighborhood of P. This implies there exists a neighborhood V of P such that V bar is subset or equal to W. Put a V equal to X minus W bar. Now W bar is subset or equal to X minus C, which implies X minus C is subset or equal to X minus W bar, which implies C is subset or equal to X minus W bar, which implies C is subset or equal to U. Now the intersection, common intersection U bar and V bar. Consider U bar intersection V bar. What is that? This is equal to X minus W bar intersection V bar, which is subset or equal to X minus W bar intersection W, which is equal to phi. That is what the necessary part, or it proves the necessary part. Now coming to the converse part, it follows directly because U bar intersection V bar equal to phi implies that U intersection V equal to phi, or the result follows. Next result or next statement or definition is what is the completely regular space. What is a completely regular space? A T1 space X2 is a completely regular space or a Tikhonov space. A Tikhonov space provided that whenever C is a closed subset of X and P is an element of X such that P not an element of C, then there exists a continuous function f from x to I, where I is closed interval 0, 1, such that f of P equal to 1 and f of x equal to 0 for all x in C. It is f of C equal to set 0, mapped on to 0. I'll repeat, completely regular space or a Tikhonov space. Actually T 3.5. That's what a Tikhonov space. A T1 space X2 is a completely regular space or a Tikhonov space provided that whenever C is a closed subset of X and P is an element of X such that P not an element of C, then there exists a continuous function f from x to 0, 1 such that f of P equal to 1. And for all x in C, f of x equal to 0. Show that question is given, show that every metric space XD is completely regular. How to show every metric space XD is completely regular? Let XD be a metric space, let C be a closed subset of X, and let P is not an element of C. Define f from x to I. How? By f of x equal to minimum of dxc divided by dpc and 1. Clearly f is continuous. And what is f of p? Minimum of dpc divided by dpc1. That is minimum of 1 and 1. That is equal to 1. Let x in C, which implies dxc equal to 0. Therefore f of x equal to minimum of 0 and 1. That is equal to 0. That is fx equal to 0 for all x in C. Hence xd is completely regular. Next theorem, that is every completely regular space is regular. Every completely regular space is regular. That's also important. Proof, let X2 be a completely regular space. Let C be a closed subset X and P not an element of C. Then there exists a continuous function f from x to 0 closed interval 0 1 such that f of p equal to 1 and f of x equal to 0 for all x in C. We have taking the semi-closed open interval 0 1 by 3, that is equal to open interval minus 1 1 by 3 intersection closed interval 0 1. Similarly, semi-open closed interval 2 by 3 1, that is intersection of 2 by 3 2 and closed interval 0 1, that is open interval 2 by 3 2 intersection closed interval 0 1. Here semi-closed 0 1 by 3, semi-closed open interval 0 1 by 3 and semi-open closed interval 2 by 3 1 are open subsets of I. This implies inverse of these, and f inverse 0 1 by 3 and f inverse 2 by 3 1 are open in X because f is continuous. We put u equal to f inverse 0 1 by 3 and v equal to f inverse 2 by 3 1. Clearly, p is in v and c subset are equal to u. Moreover, u intersection v equal to 5, hence x2 is regular. That is, every T4 space, every completely regular space is regular. Every Tikno space is a T3 space. That's what I have proved. Next theorem, a subspace of a completely regular space is completely regular. That is, subspace of a Tikno space is again a Tikno space. You can discuss or you can try for its proof. It's given as homework. Next theorem, complete regularity is a topological property. A very important theorem. Complete regularity is a topological property. Or Tikno property is a topological property. Proof, let x2 and yu be topological spaces and f from x to y be a homeomorphism. Let x2 be a completely regular space. We have to prove that yu is a completely regular space. Here x2 is t1. This implies yu is t1. Let p in y, let c be a closed subset of y such that p is not an element of c. Here f inverse c is a closed subset of x since f is continuous. Also, f inverse p is not an element of f inverse c. But x2 is completely regular. This implies there exists a continuous function g from x to closed interval 0 1 such that g of f inverse p equal to 1 and g of x equal to 0 for all x in f inverse c. That is, g of f inverse c equal to 0. Put h equal to g composite f inverse. Then h is f continuous function from y to y to closed interval 0 1. And h of p, that is g composite f inverse of p, that is g of f inverse p is equal to 1. h of c equal to g composite f inverse of c, that is g of f inverse c is equal to set 0. Hence, yu is a regular space. The topological space yu is a regular space. Therefore, we are getting yu is completely regular. We get yu is again completely regular. Or whenever x tau is a completely regular space, and f from x to y is a homeomorphism where yu is a topological space, then it follows that yu will be again completely regular, or we proved that complete regularity is a topological property. That's all about this section, the second section, that is regular and completely regular spaces, and it is 9 pages notes. It's also given here. You go through the video properly, refer the notes, and any confusion means we can discuss in the class.